Thank you for joining us today for this virtual event with the TechGirls program. My name is Briana Horton, and I am the Protocol Officer and Public Affairs Specialist at Goddard Space Flight Center. I would like to welcome you virtually today, and I am very glad that we could work out an event for this group this year. Let me take a moment for some housekeeping information before we start the event. First, if you require closed captioning, please hover over the CC button at the bottom of the video screen and click the button. If the closed captioning does not work at this time, closed captioning will be provided on the recording shortly after the conclusion of the event. Closed captioning is done through a third party, and NASA does not have any control over it during the event, but we try to make sure that the recording gets out as soon as possible. Second, after the conclusion of the panel, we will be hosting a live question and answer session with the panel members. The chat feature is enabled, so please use it throughout the entire panel, and we will try to get to as many questions as we can during the session. Now, I would like you to sit back and enjoy a short video to kick off our event today. Please roll the video.
At NASA Goddard, we build space telescopes
to explore the evolution of galaxies, stars, and planets that make up our universe.
We develop autonomous spacecraft navigation using millisecond pulsars as celestial beacons.
To further deep space exploration into our solar system and beyond.
We discover planets around other stars and investigate whether they can support life and what that life might look like.
At NASA Goddard, we investigate the possibility of past or present life on Mars.
We imagine, then engineer far-out missions to answer questions about how galaxies and planets formed and evolved over time.
We build instruments that visit every planet in the solar system
and recreate planetary environments here on Earth.
At NASA Goddard, we study the sun's dynamic behavior and the space weather that it generates so we can protect astronauts and satellites in space as well as our technology on the ground.
We use the Earth's magnetic field as a laboratory to understand the process that drives giant explosions across the whole universe.
At NASA Goddard, we use the data from a constellation of satellites to generate global maps of rain and snow pummeling the Earth.
To monitor how greenhouse gases move through the atmosphere.
And to model all of the Earth systems to create a dynamic portrait of our planet.
We survey Earth's forests, ice sheets, and oceans from air, ground, sea, and space.
And collect data to examine changes in the environment to inform and improve the lives of every human being.
We develop high-powered lasers to map our own planet and other bodies deep into the solar system.
At NASA Goddard, we launch balloons with an 8,000-pound suspended mass soaring into the atmosphere
for weeks at a time to study black holes and gamma ray bursts.
We launch small rockets carrying university-developed experiments into space.
And provide low-cost space platforms for testing new instrument concepts and engineering techniques.
At NASA Goddard, we develop and maintain communication links between Earth and spacecrafts in orbit.
We evaluate and improve system software to reduce risk in our missions, large and small.
We take the search out of search and rescue by developing technologies for global distress systems.
At NASA Goddard, we ensure every craft is space ready.
We blast noise and shake instruments to simulate stresses at launch.
We expose them to the unforgiving vacuum of space and to the powerful magnetic fields.
At NASA Goddard, we innovate robotic technologies to extend satellite lifespans.
We mentor thousands of students each year who will become the next scientists and engineers.
Innovation and science never sleep.
And new discoveries never get old.
At NASA Goddard.
I know that this video was a very short introduction into the breadth of Goddard, but I hope that the panel members can shed some light on the amazing work that we do here every day. Before we get into the panel, please let me introduce a special guest for some remarks. I would like to invite Ms. Callie Ward, Branch Chief of the Youth Program at the Bureau of Education and Culture. Ms. Ward?
Thank you, Briana, and thank you, NASA Goddard. What a treat to start the day with you and with all of you amazing tech girls. I have to say that a morning like this highlights why I love my job. As Briana mentioned, I work at the U.S. Department of State's Bureau of Educational and Cultural Affairs, or ECA. At ECA, we are committed to building mutual understanding between Americans and citizens of other countries through international exchange programs. TechGirls is just one of a number of ECA-sponsored programs and initiatives aimed at empowering women and girls. We invest in these programs as a way of investing in a better, more peaceful and prosperous future for everyone. Earlier this year, on International Women's Day, Secretary of State Antony Blinken remarked that the United States is prepared to support and advance the health, economic, political, and human rights of every woman and girl, because when women are empowered, we are all better for it. Secretary Blinken wasn't talking specifically about tech girls when he said this, but he could have been, because this program is making us all better. Whether you are currently in one of our participating countries or in your US state, you tech girls are demonstrating why we do what we do. And even virtually, the connections that you're making will have a profound impact on you and on the people you meet. And that really is the essence of what we do with programs like TechGirls. Secretary Blinken also said that when we support women, we can help foster change on a much broader scale, because it's often women doing the hard work to make that change happen. Again, he's exactly right, and here you are making that change happen. I must mention to you all how deeply grateful ECA is to partner with Legacy International, and a special shout out to Mary and all the great embassy colleagues on TechGirls. But I have to say also my colleague, Sarah Shields, who has managed this program for you this year, and actually every year since the program began. She's a real TechGirls hero. And lastly, remember that you will be joining hundreds of alumni of this program alone, not to mention hundreds of thousands of ECA alumni all over the world, including the wonderful Tech Women alumni. What a resource. So you're joining an immense network. Take advantage of it. Keep building on this program and keep building your networks. And of course, keep in touch with us. Thank you so much.
Thank you, Ms. Ward, and thank you for sponsoring this program here today. Now I would like to invite Dr. Dalia Kirschbaum, Chief of the Hydrological Sciences Laboratory at NASA Goddard Space Flight Center, to make some welcome remarks. Dr. Kirschbaum?
Well, thank you so much. It is such a pleasure to be with you today virtually. And I hope that the panel that you're about to hear is as inspiring as I am by all of our speakers. But first, let me tell you a little bit about Goddard and NASA. Now, Goddard is home to the largest collection of Earth and space scientists in the world. And we work on big missions like the James Webb Space Telescope, which will be launching this fall, Hubble Space Telescope, as well as many pioneering satellites, such as the Landsat series, which has been looking at our Earth for over 50 years, exploring our own changing planet. Through engineering, satellite missions, and research at NASA, we work with partners around the world to study how the universe is formed, how galaxies and stars evolve, how black holes collide, how our sun impacts our space weather that can influence us here on Earth, and how we can better understand our own changing planet. Now at NASA, we work as a science agency across the spectrum to develop and build, launch, and analyze satellite missions. So first, we focus on the science questions. We start with the science. We work with engineers and project managers to form the requirements and the technology needed to build those satellites. We then build the satellites working with industry and other partners and launch them into space to provide data that's free and open to people around the world to then study the science and learn new things about our universe and our home planet. And, let me start a little bit also with my journey. So I came from a town outside of Minneapolis, Minnesota, and I really loved math when I was a kid. And when I went to college, I wasn't sure how to apply that math, but I really fell in love with environmental science, the study of how things move on our Earth. I went to get a PhD and really gravitated towards how we can use satellite data to understand natural disasters around the world, hurricanes, landslides, etc. And I had the fortune of coming to NASA as a postdoctoral fellow, where I've been ever since for about the past 12 years. And I've grown into the role, continuing my research in natural disasters, also working with programs that connect with partners all over the world to build capacity to use the satellite data. I work with satellite missions, and I really have the fortune to also talk to the media, talk to people like you to inspire, hopefully, some of the great things that we can accomplish. Now, I am so thrilled to be part of this, and I'm even more excited to pass this back to Bree to introduce our tremendous panel of women today. So with that, thank you so much, and Bree, please introduce our panel.
Thank you, Dalia, for your remarks, and thank you for coming back later during the panel to moderate our Q&A session. Now on to the main event. I would like to introduce to you our panel members today. First, to discuss our work in Earth science is Aprille Ericsson, the new business lead for Instrument System Technology Division. Next is Zheng, a space weather scientist and forecaster, who will be discussing Goddard's work in heliophysics, or the study of the sun. We will then learn about our planetary and lunar studies with Stephanie Getty, the Deputy Director of our Solar System Exploration Directorate. Nzinga Tull, a Hubble engineer, will discuss Goddard's role in astrophysics. Finally, Zakiya, I'm very sorry, I apologize for my pronunciation. Tomlinson, a robotic engineer, will talk about Goddard's role in technology and robotics. This is going to be an amazing event today, and I am happy to turn it over to Aprille to kick things off. Aprille?
Good morning, everyone. Thanks for inviting me to here today. I just love speaking to women and students and scholars all over the world, and so I appreciate you guys. I'm assuming that it's probably later in the evening there, so I'm saying good morning to my U.S. colleagues, but I'll say good evening to the other invitees. So let's start it off really quickly. I'm going to try to go through a little bit about myself. I've had a very varied career at NASA Goddard Space Flight Center, but I'd say largely from the perspective of the agency. I've done a number of things, from engineering to really being also a professor at a university, as well as managing large instruments for our missions. And then I am also a mom. So I say we can do all that, young ladies. Let me just give you a little bit of smattering of some of the things that I've been able to accomplish. I've had a number of awards that have really pointed out the fact that I've contributed not just to the science that we do at our centers, but also to education. I sit on multiple boards. And let me tell you, I am from the perspective of the United States, an East Coast girl. I grew up in Brooklyn, New York, and then I moved on to high school in Cambridge, Massachusetts. I attended MIT for my undergrad, and then later on I moved to Washington, D.C., where I currently reside, and I attended Howard University. So let me just tell you a little bit about those experiences. Oh, and by the way, that picture, the second one, I wear hats a lot, but the second one was a picture that was taken while I was a junior in high school. I was in a special program at MIT, and we had a bridge competition in that summer program. That picture ended up on the front page of the newspaper for the university, and I thought, maybe this is a place that I might want to attend. So I've had a varied experiences at the collegiate level, but I was also fortunate to work on supporting contracts and grants from other institutions like the Air Force, NASA Langley Research Center, which is another facility that's not that far from, it's actually about 4 hours from NASA Goddard Space Flight Center. My work and research was really focused on large space structures like the International Space Station. I also attended special summer activities with Harvard. So I went from one side of Cambridge, Massachusetts to the other side of Cambridge, Massachusetts, attending that university as well. Some of the things that I've been so lucky, I heard one of our speakers say they were here 12 years and I thought, you're young, because I've been here now 30 plus years with working with NASA. I started very early in my collegiate career and then spent the majority of my career here, but also worked at NASA headquarters. So it just shows you from doing very intricate engineering work to later moving on to the management positions that I currently hold. So our other professor, or I guess I want to say researcher from Heliophysics, mentioned that how we actually support science, and there you can see we actually support 4 different science areas, but myself as an engineer, I'm really partnering with the scientists to achieve the capabilities that we currently have. I work in the Instrument Systems and Technology Division, and these are some of the major focus areas for our technology. So as you can see, there's the James Webb Space Telescope mirrors, the pretty gold mirrors that you see that look like a honeycomb. We do lasers, we do cryogenics, we do detector technology along with the optics that I mentioned. And we're very fortunate to be able to support the science instruments that you'll hear about today. So I'm going to focus a little bit on earth science. That is one of the main areas that I've contributed. I've done, when I was an instrument manager, I helped to develop the ISAT-2 instrument, which was Atlas, and it was contributing to the science that we currently understand for climate change, looking at ice sheets. I'll show that in a video in a moment, but I really wanted to let you understand that there are so many facets to earth science. There are a lot of forcing functions that occur that really contribute to our climate and the variability that we see in our everyday weather patterns or yearly patterns as well. As an engineer, I was working initially on attitude control systems, so really looking at how we control spacecraft and putting them into the position and locations that will provide us with the data that we understand. And so for you, you probably have a personal device that you see your weather on, or you listen to it on the news in the morning, but we have this infrastructure of spacecraft and then ground measurements that help to contribute to our understanding. And so we have this wonderful fleet of Earth science spaceflight missions that help us to really be able to observe the Earth. And so one of my favorite, which I mentioned before, was Atlas. But prior to that, I was actually on a lunar mission, Lunar Reconnaissance Orbiter. The LOLA instrument also is a laser altimeter. And you'll get to see in a moment how those measurements are made from the sky. It is so important for us to understand how our planet is changing. And so you can see there at the bottom, they're showing you how the ice sheets in the pole areas are actually receding. And I also mentioned on this slide how we also look at things like tropical weather, hurricanes, with some of the other observing capabilities. So moving on to ISAT. Not only does ISAT measure the ice, it also looks at the topography of trees. And I'm hoping that this video will play. Maybe it needs to be clicked on. Let's see. Okay, awesome.
Data, we have a very good handle of how our Earth looks like. We can see oceans, we can see the sea ice, we can see our forest. What is much, much harder to measure is how high things are on a global scale, almost impossible.
ISAT-2 adds the third dimension, the elevation. Repeating measurements from ISAT-2 will allow us to measure changes in the ice sheets or in the ocean or in land.
Just so you guys know, it's a 2-minute video.
To measure the changes that are going on in the cryosphere, in the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ISA-2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ISA-2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate
so what I see on my video feed, I don't currently see, so you'll have to let me know the end of the movie.
Those areas and will help us to understand what's going on with our planet.
So thank you everyone for listening to a little bit of my story. I look forward to hearing the other panelists tell and share their story. Dr. Zheng?
Thank you, Aprille.
New ways of measuring time very precisely. A billionth of a second translate to...
Sorry, I was still hearing Aprille's video.
Elevation change precision of just a few centimeters.
Hi, everyone. It's a great pleasure to be able to speak to you, ladies. And for my personal story, I grew up in China, and where education and science is highly valued. And then I came to the US in 1997, got my PhD from University of New Hampshire. In 2001, then I came to Goddard as a postdoc. Then I went to Johns Hopkins Applied Physics Lab to continue work as a scientist. And then in 2010, I came back to work as a civil servant. So my area of research is heliophysics. So today I'm going to just talk a little bit about the heliophysics. So heliophysics is really a study of the sun and how it interacts with the nature of the space and the atmosphere of the planet, especially our planet Earth, and the technological assets existing there, like all the satellites, and sometimes also human in space. So the sun is really. The sun is normally when we think about the sun, the sun provides the light and the heat that's sustaining life in Earth. But for the heliophysicists, we want to know how that affects Earth and the dynamics within, and the changes that affect the sun, Earth, the whole environment. So it's great to be a heliophysicist. Not only, it offers exciting science, but it also has this duality. It has practical applications, like the weather in space affect the satellites and other assets, as I mentioned. So normally the sun, constantly from a physicist point of view, constantly spewing out of a large material called the solar wind. So those materials are the charged particles and carries with them the magnetic field. So normally it's inhomogeneous, but at the constant speed, at times it has large eruptions. Those eruptions can like solar flares and large coronal mass ejections, and those can cause space radiation. Then space radiation can affect human in space. And all these, spectrum of solar activity interact with the Earth can cause a slew of the phenomena, including the beautiful aurora you can see from the northern high latitude or in southern high latitude, Antarctic region. So the dynamic environment resulting from this condition is called weather in space. So as scientists, we study the science and also the weather can affecting, as I said, the assets, including the spacecraft hardware, solar panels, and affect human in space. And also when it's interact with the Earth can affect communication, navigation, like a GPS accuracy. Sometimes if the interaction is so strong, it can wipe out part of the power grid. So this, I see it as an exciting branch of science. I mean, for a number of years, I've been involved in providing space weather services to all NASA robotic missions, and also educating high schoolers, professionals, and also forecasters in this complex, about these complex interactions and the science with it. And next, I want to show you, the sign goes through the solar cycles, and this, the last solar cycle, 24, ends December 2019. And this, so after like January 2020, is starting a new solar cycle called solar cycle 25. So this one really shows the example of a solar storm. So you see these are the instruments. You see a eruption from the sun, then there's a signature of that eruption, and this is a modeling of that eruption. This is not the biggest storm we have seen, but it's happened recently in May this year. And this you can see from a large physics-based model, the response of Earth, our Earth's magnetosphere, because Earth has a magnetic field response to this storm. And this KP is a indicator of how disturbed, how strong that storm is. So it's just show you a little flavor of that. So for the heliophysics science division at Goddard, we have 5 labs throughout the science domain. We have 200 plus scientists, working in different areas of this complex system and performing the cutting edge research. We have data analysts and also theorists and modelers modeling different aspects of this domain. And we have experimentalists, instrumentalists, build the different detectors to measure things more innovatively. And also I'm a member of the community called Modeling Center, which holds the largest collection of space science and space weather models. So we provide the model service to the whole community, international community, and so they can put the science in a global perspective. Then also we have a new Moon to Mars office to support future human exploration mission to Mars and the Moon. And the scientists serve as project scientists, the mission principal investigators, and community leaders. Serve as, also the educational activities and to inspire next generation and so on and so forth. And I also want to say heliophysics really has a lot of connection with other branches of the science we do at NASA with the panelists later on their work. We have close collaboration with, say, planetary scientists and astrophysics and earth science. There are a lot of commonalities, and also, you know, the sparkling of interdisciplinary research can inspire big ideas and new science. And also recently, Heliophysics also recognized the big data, the artificial intelligence, how that can be applied to heliophysics to, you know, discover more things. These are the missions devoted to heliophysics. I just want to show briefly. And what's cool also, the science stamps. So that recently, because of the SDO, the Solar Dynamic Observatory mission, we have a lot of high-res images of the sun, the beautiful things. So the U.S. Post Office issues this forever stamps. So depicting different aspects of solar activities, use the dark region, it's corona holes where the high-speed stream coming out. Then there's also flares, that's like the brightening on the sun, that's electromagnetic radiation. And then you have also those large eruptions, the loops. So that's a good recognition of the importance of the heliophysics. And here I provide some links where you can learn more about the heliophysics and the division at Goddard, work we do. Thank you. Next, I think it's Stephanie.
That's right. Thank you so much. I am so happy to be here with you today. I hear a little bit of an echo, but hopefully yes, that's getting better. Super. Yeah, I'm the Deputy Director of the Solar System Exploration Division here at Goddard, and it's so great to be part of this virtual event with all of you today. I started out my career as a solid-state physicist, and I'm really excited to be able to apply my love of all the disciplines of science to a career in planetary science. For this session, I'm going to focus on kind of the range of planetary science that we do in the Solar System Exploration Division at Goddard, but hopefully I'll see some of you in the mentoring session next. So, you know, it's actually hard to summarize all of the work we do in the division in a short amount of time, but generally we study the planets, their moons, the small bodies of the solar system, and we even work to study planets in other solar systems called exoplanets. Our science ranges from forming new theories and models, conducting experimental research in our laboratories and in environments on Earth that mimic environments on other planets. We send missions and instruments out into space to answer the big questions that only missions can answer. And the truth is, for every answer we get, we come up with many more questions to ask. That's science. Let's see, I am, making sure that my slides advance. Super. So I'm going to take you on a whirlwind tour of the major mission efforts we have going on right now as a way to kind of step through the science that we do. But I want to convey that there is a whole lot of theoretical and laboratory work behind most of these efforts to really help us interpret our results. So let me start with the asteroid belt and OSIRIS-REx. This spacecraft set the record for orbiting the smallest object ever, asteroid Bennu. And it did better than that. It very carefully descended, touched the surface, and grabbed some sample from Bennu. This sample is going to be returned to Earth in 2024 and represents material from the very beginnings of the solar system. By analyzing these samples on Earth with amongst the science community at large, we'll learn how these so-called primitive bodies may have contributed important chemicals to an early Earth as life was taking hold here. Next, we have 3 Mars missions, either in operations or getting ready to launch. Our instrument SAM has been analyzing, on the left-hand side, has been analyzing surface samples from an ancient lake bed on Mars. It's been operating for about 9 years now as part of the Curiosity rover. MAVEN in the center is an orbiter around Mars, and it's studying how the atmosphere is being lost and how the upper atmosphere behaves under the influence of the sun. And on the right, a team here at Goddard built the central part of a mass spectrometer, MoMA, that will explore chemical evidence of past life that Mars may have preserved at a depth up to 2 meters under the surface. ExoMars and MoMA are going to launch late summer of next year. Looking forward to that. Oh shoot, I think I went too far. Forgive me. Thank you. Okay, let me tell you now about our upcoming missions that are still being built here on Earth, but taking a lot of science to do it. Launching in mid-October of this year is the Lucy mission. This is led out of Southwest Research Institute with science participation and an instrument built by our group in our division. This mission will visit 8 asteroids, including 4 binaries, and take images and spectra of these unusually red asteroids called Trojans that reside near Jupiter to discover their origin and composition. They're different from the rest of the asteroid belt. We're also building 2 instruments and providing science leadership for this exciting Dragonfly mission. Dragonfly is going to explore Saturn's moon Titan from a quadcopter platform. This moon in the outer solar system is a fascinating world of clouds, a surface at extremely cold temperatures, methane and ethane lakes that form and change seasonally, and teams in our group will send these instruments to help discern the composition of the surface environment from being there. We're also sending the first in-situ mission to Venus since the 1980s. We just recently learned that Da Vinci has been selected as NASA's next discovery mission. We'll be taking a carrier spacecraft and a spherical probe to study Venus from above the clouds and then throughout its atmosphere. We're going to discover whether Venus was ever an ocean world, more like Earth in its past. This mission is led by Goddard, and I'm actually privileged to be one of the deputy principal investigators of this mission. We'll also build a critical instrument that will be carried on the probe. So exciting. All right, now we'll also go back to Mars with participation on the capture, containment, and return system element of the Mars sample return mission campaign. We'll have input into sample collection sites. And with the samples returned to Earth from the Perseverance rover, the experimental community will be able to conduct really sensitive measurements for a whole new understanding of Mars. In the Mars Ice Mapper to study the extent and distribution of water ice in the polar regions of Mars. Finally, the agency is going back to the moon with crewed missions in the 2020s, and our talented team of lunar scientists, field explorers like you see on the left in an analog environment on Earth, and instrument developers in the division are working to develop plans for conducting science in support of the Artemis program. So that doesn't cover it all, but our division and scientists are incredibly dedicated and productive in forging a new understanding of our solar system. I want to point out it takes an interdisciplinary, diverse team to do these big things. We work across international lines in many, many cases. And I hope you're as inspired by our science as I am every day. Thanks so much. And now I'd like to hand it over to Nzinga Tull to tell you more about astrophysics at Goddard.
Thanks. One day I'll get a hang of that. Thank you. Hi, thanks, Stephanie. It's great to see everyone and to hear all of my colleagues at NASA. Again, my name is Nzinga Tull. I'm a contractor here, and I am currently supporting the Hubble Space Telescope program, which is one of the flagship programs at the astrophysics here at Goddard. This is actually my second tour on Hubble. I started in my career right after graduating from Spelman College, which is a historically Black women's college in Atlanta. In 1998, I came and started working with Hubble in the Power Group, and I moved into systems management and systems engineering. Then I moved away for about 8 years and just rejoined the Hubble team because Hubble's still going strong. So I'm really excited to talk about some of the work that I do and some of the other missions in astrophysics here at Goddard. So astrophysics essentially asks three major questions. How does the universe work? Like how did we all get here? Astronomers frequently talk about dark energy, and that being that mysterious, powerful force that is constantly pulling the universe apart, the ever-expanding universe. So just figuring out the roots of how we got here, the roots of how the universe works. And then, of course, for us on Earth in particular, how did we get here? How did our solar system form? And how did the celestial bodies in our solar system affect the other celestial bodies, stars, galaxies, and so forth? And then finally, are we alone in the universe? Are we on Earth? Is there other life on other planets and other bodies? And how can we possibly learn from them and connect with them? So those are the three major questions that many of the missions in astrophysics are looking to, in various ways, with various approaches, looking to answer. As I mentioned, I've been supporting Hubble for about 13 years at the beginning of my career, and then I rejoined the program about 3 years ago. Hubble is one of NASA's great observatories. We are currently in our 32nd year of operation. We were originally planned to function for 15 years, so now we have more than doubled that. Hubble is about the size of a school bus. It orbits the Earth at about a height of about 340 miles above the Earth's surface. And Hubble essentially revolutionized the astronomy across the board. What was special about this and other space-based telescopes is that because of the position of Hubble above the Earth's atmosphere, it's not subject to the distortions of the Earth's atmosphere. And so it allows us to have a crystal clear vision into outer space. And we didn't have that kind of breadth and depth before Hubble launched back in 1990. And we also, through the course of the program, have revolutionized servicing. When the space shuttle was in use, we took advantage of the astronauts in the shuttle program and periodically went up to have servicing missions where we would fix broken support parts. We'd also make sure we'd update the science instruments so that we had the most powerful complement of science instruments on board. And it's been a game changer for the astronomy community. We have had over 18,000 science papers have been written based on discoveries made from Hubble. There have been well over 1.5 million observations, and we're still fielding applications from astronomers all over the world and at various levels of their careers, looking to use Hubble to learn more about our universe. You may have heard we had, it's been an exciting summer for us on Hubble. We actually had the payload computer at the beginning, around mid-June, had stopped working. And usually Hubble engineers, we're pretty proud of ourselves. We're usually able to recover the telescope in a matter of hours. Sometimes it takes a matter of days, but this was a much more extensive issue because of the age of the telescope and the complexity and design of the telescope. And we were actually down and hadn't done science for a month when we were trying to identify the problem with the payload computer. But fortunately, a week or so ago, we were able to understand isolate where we thought the root cause of the problem was, which was a power distribution unit in one of the computers, and figured out how to reconfigure the entire telescope so that we can restore its functionality. And these images that you see on the screen here are the first images that we had taken after Hubble had been down for about a month. The next slide shows two of my favorite images. One of the things about Hubble is that the science that is collected is presented so beautifully. I'm not an astronomer, so I don't have the analysis about galaxies and dark matter and the nebula, but I can appreciate how aesthetically gorgeous they are, and also appreciate just how the breadth of expertise that the science community that we support uses to help expand our understanding of the universe. So the Hubble team at Goddard is responsible for making sure that the telescope is working, that it's thermally safe, that it's pointing in the right direction, that all of the power is being distributed evenly, and so that the Hubble instruments can take the science that the astronomy and the general public know and love so much. So again, Hubble is in its 32nd year of operation, and the mission operations team is completely dedicated to making sure we keep it operating for as long as possible. There are still many astronomers who appreciate the science that we do on Hubble. And there are also some next generation telescopes. As Dr. Aprille mentioned, the James Webb telescope is set to launch later this year. And it'll be an amazing complement. It'll have a deeper reading on the infrared region. Hubble monitors collects data from both infrared, ultraviolet, and the visible light spectrum. So James Webb is coming up momentarily. And then finally, we have the Nancy Grace Roman telescope. It was the W-FIRST program. And this is another infrared telescope that was recently renamed for Nancy Grace Roman, who was a woman who joined NASA months after the NASA was formed, and it really was a leader technically in terms of her technical expertise, and also advocating for diversity and equality in the way that we approach astrophysics. She's also known as the mother of Hubble. She was critical in bringing together a panel of engineers and scientists to study exactly why we needed a space-based telescope like Hubble. And she was very important in lobbying Congress to make sure that we had the resources allocated. So space study of the universe is the focus of the astrophysics division, and the future is bright given all of the work that continues to happen. It's lovely hearing from everybody, and now I'm going to hand it over to Zakiya.
Thank you very much. Good morning, everyone. My name is Zakiya Tomlinson. I'm a robotics engineer here at Goddard. I grew up in this area, and back in high school, one of my teachers entered my class in a robotics competition. I had no idea at that point that robotics would become the focus of my career. I had a different plan for my life, but I stayed open to new ideas and took advantage of opportunities during college and grad school. I started my career as a robotics instructor for the International Space Station program, and now I can't imagine working on anything other than robotics. So I'm really happy to be able to talk to you about the past and future of the robotics work that we're doing here at Goddard. As we're talking about, Hubble Space Telescope is one of NASA's most important achievements, not only for teaching us about the universe, but also opening our eyes to the new types of work that we can do in space. The space shuttle brought astronauts to fix and upgrade Hubble 5 times. And you can see in the picture on the left that each time the astronauts were assisted by a robotic arm in order to do their mission. So this was the origin of the group that I work for, NASA's Exploration and In-Space Services Projects Division. The engineers who had worked on Hubble servicing missions started thinking about what could come next. How else could we use the technology and the techniques that we had learned about in space? And so that has turned into a mission called OSAM-1, which will send a robotic spacecraft to refuel a science satellite that's already up in space. And that's what the image on the right depicts what that mission is going to look like. So you may wonder, why do we need to service satellites? Out of the thousands of spacecraft that have been sent into orbit and beyond our planet, some of which are shown in this image, Only two have been designed to actually be serviced in space, Hubble and the International Space Station. For all the others, when they break or run out of fuel, they're discarded and a replacement must be built and launched. This is the way that it's always been, but it's expensive and contributes to orbital debris. So being able to repair and refuel these satellites in orbit will revolutionize the industry. Just like the Hubble servicing missions, scientific instruments could be repaired or upgraded and make more discoveries possible over time. And if a satellite that has working instruments is just running out of fuel, then its lifespan could be extended by being able to refuel it. Also, when we're designing a new satellite, more mass could be used for the instruments instead of for fuel tanks if they know that they can be refueled after launch. So these shows the place that I'm lucky enough to get to work. These are our test facilities at Goddard. Robotic missions require a team of people who are experts in many different areas working together. Mechanical and electrical engineers and material scientists are the ones to design the robot arm. They have to balance the needs to make it lightweight, strong, and able to survive in the space environment. Our software developers write the code to be able to control the robot. They also model and program simulations of the robots and their environment that we use for testing on the ground. I'm one of the robot operators. We actually use the robots to evaluate the tool designs and the software and plan out how we're actually going to do our tasks in space. And we have electricians and technicians that set up all of our equipment and keep the facility running. I was actually the one operating the robot when they took the picture on the bottom left. We do a lot of different testing in our facilities, and we also have to make sure that everyone in the facility is safe as we're working on these really large systems. So I also run our training and safety programs. Most of us have more than one thing that we're interested in and divide our time between various different responsibilities. I really love the fact that there's no such thing as a typical day at work. There's always something new and interesting that's going on. One of the best things about our work is getting to develop new technology and figure things out for the first time. Some of the examples are how do we use cameras and program the robotic arm so that the robot can see what's happening in front of it and move on its own. That's what's happening in the top video. The robot on the right has to find the correct spot to grab onto and actually kind of drive itself to be able to do its task. We also try and figure out how do we do things like cutting wires or taking off caps in space, which you'll see in the lower videos where we're removing a cap. So many things are different without gravity. You don't want the cap to float away when you let go, or you don't want wire fragments to come loose because they can get stuck in something else and break your hardware. We do a lot of testing. I really enjoy seeing how something works and considering how to make it better. Sometimes it takes 1 or 2 or maybe 5 tries to get a design right, but we go through the process and make a lot of notes, talk to each other about what's the next best plan, and then go through and do testing all over again until we get it right. And we want our tests to be as realistic as possible, so sometimes we use underwater testing or even send prototypes into space. The pictures on the right show testing that we did on the International Space Station. We used their robotic arm to test out tool designs for our mission. The members of our team, love to figure things out and to learn. So then it's important for scientists and engineers to always keep asking, what can we take from what we're doing now to make something else better in the future? And space robotics, I think, has a really bright future. Robot systems can be used to help maintain or repair habitats on the moon or Mars, or the spacecraft that the astronauts will use to get to them. And robots can also help us construct new technology to continue learning about the universe, like telescopes that are too big to fit on a single rocket. They can be launched in multiple pieces and then put together in space with a robotic arm. And the robots can also help us bring back samples from places we can't yet send people to, like asteroids, comets, or other planets or their moons. Stephanie mentioned earlier the mission to return samples from Mars. A robotic arm will be used to safely pack those samples into a spacecraft to get them back to Earth. Or maybe the next big mission idea is something we haven't thought of yet, but it's a dream of a student like you guys. So we're really interested to see what comes next and who else is going to be joining our team in the future. So thank you guys very much.
Well, thank you so much for these inspiring presentations that really cross the gamut. I hope that you have learned something. I know I have. We have a few minutes to jump into a couple questions with the panel. And so the first one I wanted to make sure that we asked, and I'll invite all of our panelists to give a short answer, is what advice do you have for tech girls who are interested in entering your field? And what can tech girls do to start getting involved in STEM careers as high schoolers? Why don't we start with Nzinga? Would you like to talk to that, and we'll kind of go around?
Super quickly, I think that you should honor the things that interest you. Find a friend, so have a peer who hopefully shares similar interests, and find a mentor, someone who's older and more experienced and who can help you move along. But always stay connected to that passion, the thing that you think is interesting, and then find your community who can support you in developing it.
Excellent point. And the mentor part was really a strong reason why kind of I had my track too. So absolutely. Aprille, would you like to give some thoughts?
Sure. So I think I'll piggyback off of a question that was asked about math. Students are asking, do I have to like physics? Can I just do math? And I think math is one of the integral pieces of sort of understanding a lot of things that occur in our universe. So a great foundation in math is very, very important. And so I would say, keep working on your math, because I think it's across all of the different disciplines. So that would be my tip.
Here to that. Basic math and science courses, do them now because you can do way cooler things later. Zakiya, what are your thoughts?
I would say one thing is don't be afraid of things that don't come easy to you. Going back to math and physics, I don't really think I was very good at either of them in high school, but I worked hard at them because I know I needed them for what I wanted to do. So things don't have to come easy if you're willing to work hard.
Excellent point. Thank you. And Yihua, what would be your takeaways?
Yeah, I would say, don't be afraid of the hard things. And also, there are so many resources now available. The internet just provides you wealth of information. Just dive into it and learn. Like go to NASA website, go to some other academic institute. You are interested in some subject, and just Google it. So Google is your friend, but of course you have to trust the resources. But I think there's a great, great resources available there to learn, and also the mentoring is important. But I think just be self-motivated and learn, absorb, and don't be afraid. Like even contact. You see some professor, their work, their things interest you. Contact them. I mean, they will be very pleased to help you out. So just learn.
Yeah, excellent point. Absolutely. Stephanie, what do you think?
Yeah. Oh, I almost can't add to all of the great responses so far, but I just wanted to say that in my career anyway, and I think it's true generally, is that you're going to encounter a lot of what seem like really hard choices between different paths in your career. And so I just wanted to convey the message that if you stay true to what you value, and if you stay true to what you love and are passionate about, then there are really no wrong answers to making these hard choices. And I also wanted to echo what Nzinga mentioned. I think about peer mentoring specifically. I think peer mentoring might be as important or more important than mentoring from the more senior members of the group around you. So I'd really encourage you to pursue that. Support each other.
Absolutely. And I think keeping on that theme, we've had some great questions, and unfortunately, we're not going to be able to address them in the panel, but we're going to close this session and move on to the mentoring session. So please don't be shy to ask more questions about, career paths or challenges you've overcome, different science terms that really interest you. You wanted to learn more. So with that, thank you so much to the panelists for participating and sharing your really inspiring stories. And thank you to TechGirls for dialing in. And so with that, I'd like to turn it back to Bree to give some instructions on the next segment of this. Thank you.
Thank you, everyone. This has been absolutely amazing. I've learned a lot, and I've been here for what Aprille would say was a very short amount of time, 11 years. But I do have to say that even if you are not a scientist and an engineer, but you have a passion for science and engineering, you can still work at a place like NASA. I have a degree in accounting and finance, and I still work here at NASA. So I invite you to attend your first mentoring session. You have 25 minutes. There's 2 of them. You've been assigned 2 mentors. So please go ahead and join the Teams link for your first mentoring session, and I will see some of you there. Have a good one.